Okay, so we continue from where we stopped. Thank you. So today we are looking at the, good afternoon. Good afternoon. Today we are going to look at deviation from ideal behavior. So all along we've been talking about ideal gas behavior. So we continue from where we stopped. Thank you. So today we are looking at the, good afternoon. Today we are going to look at deviation from ideal behavior. So all along we've been talking about ideal gas behavior. So we continue where we stopped. Now, gases that do not obey ideal behavior or ideal gas equation. Gases that do not obey ideal gas equation are real gases. Now, gases that do not obey gases that do not obey ideal behavior or ideal gas equation. Or is it them? Gases that do not obey ideal gas equation are real gases. The extent to which a real gas departs from the ideal behavior may be depicted by its compression factor. The extent to which a real gas departs from the ideal behavior depicted by its compression factor. So the compressibility factor is depicted, or is symbol. We use the symbol Z to represent compression factor, and the formula is Z equals PV over RT. Now, PV equals RT. We have some gases here, and we are plotting their PV over RT against pressure. Now, what's the compressibility factor is depicted, or is symbol. We use the symbol Z to represent compression factor, and the formula is Z equals PV over RT. Now, PV equals RT. We have some gases here, and we are plotting their PV over RT against pressure. Now, what's the gases we have here is hydrogen, nitrogen, methane, helium, and CO2. Now, if you look at these gases, the one that is very light is hydrogen here. The plot of these gases gives the following the following curves. The one in blue actually is the ideal gas. Nitrogen, methane, helium, and CO2. Now, if you look at these gases, the one that is very light is hydrogen. The plot of these gases gives the following curves. The one in blue actually is the ideal gas. So it gives a horizontal line because the gas is ideal and there's nothing is happening to the pressure because we have assumed that they occupy the pressure of the volume of a gas, and that the pressure, when you increase pressure, the volume of the gas is supposed to decrease. And in decreasing, it causes the intermolecular attraction of the gases to increase. Pressure, because we have assumed that they occupy the pressure, the volume of a gas, and that the pressure, when you increase pressure, the volume of the gas is supposed to decrease, and in decrease, it causes the intermolecular attraction of the gases to increase. So this causes a deep downward, especially if the gas is heavy. It causes a deep downward, which, as pressure increases, goes up again. So if you look at the light gases like the hydrogen, the okay, sorry for that break. So as I was saying, if we look at the compression factor Z is equal to PV over RT. Now PV over R is a constant. And then if we plot this PV for individual gases, PV over RT for individual gases against pressure, we'll see that for an ideal gas, the curve is we have a straight line, a straight horizontal line, showing that there's no, it does not go, we compress I have not even, showing that there is no compression here of the gas. The compressibility factor is equal to 1, which is a bit normal. Now for nitrogen, you will see that at low pressure, there is a dip formed. Why is this dip formed? Because at that low pressure, there is the gases are not, the volume of the gas is not reduced. So the gases can still move about, the gas molecules. But as you continue to increase the pressure, there's a dip here because they have started, intermolecular forces have come in, they have started colliding or interacting with one another. And after some time, as the pressure, as you increase the pressure further by trying to compress the gases together, what happens is that the curve now strikes or goes upwards at higher pressure, indicating that this is not an ideal gas. As the molecular mass increases, because you will look at, if you look at CO2 and NH2, they are the ones with, they are the heavier gases here, and they have the most deep as you try to compress this gas. So actually, looking at hydrogen is very light. And so it's almost at low pressure, you will see that it is almost behaving like ideal gas at low pressure. As the temperature increases, as the pressure increases, there is just a slight deviation from the ideal behavior. So the molecular weight of the gas has a lot to do in determining its compressibility factor in this case. And then if we plot one of the gases like nitrogen against different temperature, we will see that at very low temperature, we have the dip again. So as the temperature increases, the dip is a bit wider. The dip is reduced, showing that as you increase the temperature, the what is it called? The interaction or the volume of the gas begins to increase because the gases move faster, and the collision of these gases increases. And by the time you are reducing the pressure, because this is plotted against temperature, but against pressure at different temperature. Now look at it at very low pressure, and let's say low temperature, the dip is high here. But when you increase the temperature, let's say, look at this 300, 400, is almost becoming ideal. So what it's saying is that at high temperature and low pressure and high pressure, you have the gas almost behaving like an ideal gas. But at low pressure and low temperature, you have the gas deviating radically from the ideal behavior. So at low temperature, Z is less than 1 for moderate pressure, and at higher temperatures, Z, that is the compression factor, is greater than 1 for all pressures, greater than 1 for all pressures at higher temperature. Look at it, greater than 1, and at low, for this one, it is less than 1. This one almost 1 here. And at this point, it is 1. Looking at the 300, 400, and 300 and 400 Kelvin, it is almost 1. Now, gases become less ideal at low temperatures, but low temperature varies from gas to gas. So it is a relative thing, depending on the gas we are dealing with. Its low temperature will differ from that of another. Now, the closer a gas gets to the temperature at which the gas liquefies or solidifies, for example, in the case of CO2, the more non-ideal the gas becomes. The closer a gas gets to the temperature at which the gas liquefies or solidifies, in the case of CO2, the more non-ideal the gas becomes. The pressure and temperature effects on non-ideal behavior of gases could be understood by considering two factors that are negligible in the kinetic molecular equation. So in this case, we are saying it has deviated from the ideal behavior. And here we have been talking about volume and pressure. Volume and pressure. So we need to find out those factors which we assumed before that this real gas is not obeying. And those are the things we have to correct for. So we need to derive another equation for real gases, and by effecting these corrections on those factors. The volume occupied, we said the volume occupied by molecules of a gas is negligible relative to the volume of the container. And so there are no intermolecular attractions between the gas molecules. These were things we assumed when trying to derive the ideal gas equation. Now, the assumptions are not strictly true for real gases. So what we are saying is that volume occupied by molecules of a gas is negligible. It's not negligible in this case, that they actually have a volume. They have a volume. And then that there are no intermolecular attractions between the gas. There are intermolecular attractions. As the gas are compressed, or the pressure is increased and the volume is decreased, there is more interaction. It could be attraction, it could be repulsion, depending on the pressure you are applying and the volume we have gotten to. So these particular assumptions, these two assumptions we have made are not, have to be corrected for us to derive the equation. So the assumptions are not strictly true for real gases. They have finite but small volumes. So we are saying that they have volumes actually. And the free unoccupied spaces in which the molecule can move is somewhat less than the container volume. So the volume, the actual volume or the exact volume of the gas is actually smaller than the container itself. And this is mostly dominant at high pressure. So you notice this when you increase the pressure of the gas. Increasing the pressure means you are reducing the volume and you are trying to what? Compress the gas. Now the attractive forces between molecules come into play at short distances. So because you have increased the pressure, you are forcing the gases to come together. They are not free to move about, as in when the volume was a bit high and the pressure was low. So compressing it up, adding, increasing the pressure makes them come together. They hit one another, and at a time they begin to repel one another because of the electrons in them. So the attractive forces between molecules come into play at short distances when the molecules are crowded together at high pressure. So there is a need to derive an equation for non-ideal gases. Two approaches have been used to correct for non-ideality of real gases. The first approach is that by considering the macroscopic properties of the gas, e.g. pressure, volume, and density, we can correct that aspect of the gas, and then considering the microscopic properties of the gas, e.g. the mean free path, molecular diameter, and all that. Now, corrections are made on the pressure term and the volume term. So take note, corrections are made on the pressure term and the volume term. And so P plus, we said PV equals nRT. Now we are bringing in a correction factor for both the PV, the P and the V, the pressure and the volume. So N squared A over VT, V squared, is the correction for the pressure, while minus NB, that means we subtract to get the exact volume of the gas, we subtract. We assumed it fills the container, but there is an exact volume, which is a small portion. So V minus NB giving us N equals RT. So in this case, A and B are constants. So if given molecular volumes of the gas, we know that Vm is equal to V over N, volume over number of molecules. Then equation becomes Vm, which is V over N minus B. N squared over V squared. So if we take V over N squared, that is why it is for molecular volume, it is Vm squared. So P plus A over Vm squared and times Vm minus B is equal to RT. Is equal to RT. So the equation is known as, this is what is known as the van der Waals equation. The van der Waals equation. Now, since the collision of real gases are non-elastic, the term N squared A over V squared corrects for the interaction of these particles, while NB term corrects for the excluded volume. That's the real gas particle have real volume. So it's known as the excluded volume, correct for the excluded volume, which is after we have compressed the gas and we've gotten the exact volume of the gas, the excluded volume, the other volume which the gas occupies when the pressure is not high, is what we correct for. That's the NB. So the parameters A and B are called the van der Waals constants. Parameters A and B are called the van der Waals constants. And it is not the same for all gases. Each individual gas has its A and B, its van der Waals constant. So if we solve this example, find the pressure of 2 moles of CO2, carbon 4 oxide gas, at 298 Kelvin in a 5-liter container. The van der Waals constants for CO2 are given. A is equal to 3.592 liters squared atmosphere per mole. How did we get the unit, you may ask? Liter squared atmosphere per mole, because we are talking of volume here. Liter squared atmosphere per mole. Liter squared atmosphere per mole squared. That is our A. B is equal to for CO2, 0.04267 liter per mole. Liter per mole, because we are dealing, we said is V minus NB. N is the mole, number of molecules, or number of moles of gas, while the V has the liter. So that's how you get the units. So now you will be given, for any gas you are asked to find or you are going to use the van der Waals equation to solve, you will be given the van der Waals constant. It's not something you cram, because for every gas, it has its own A and B. So it will be supplied to you. So to solve that equation, what are the parameters given? We were given temperature in Kelvin, 2 moles of gas, 5 liter volume. We are calculating the pressure. That is what we are looking for. So P is equal to, making P the subject of the formula, we have nRT over V minus NB minus N squared A all over V squared. So if we plug in the values into the equation, we have 2 moles times 0. Now, note that for the gas constant, we are using 0.0821 liter atmosphere per Kelvin per mole. Because, was it specified? We are looking for pressure. So we need that has the pressure term. And that's why we are using the 0.0821 liter per atmosphere per Kelvin per mole times the temperature, 298 Kelvin, minus, we said N squared, and we said N is 2 moles. So 2 moles squared, which will be 4 moles squared times 3.592 liter squared atmosphere all over 5 liter minus, that's V, minus 2 moles times 0.04267 liter per mole over 25 liter squared times mole squared. So note the units, know what cancels out, and know what is left. We work out this very well. We have 48.9316 liter atmosphere over 4.1915 liter, minus 14.368 atmosphere all over 25. Now, P is equal to 9.96 atmosphere minus 0.57 atmosphere. Now, if we do that, we have our answer as 9.39 atmosphere. 9.39 atmosphere. Now, if we want to check the difference now, we got 9.39 atmosphere using for the real gas. Now, if we had used ideal gas equation, we will get 9.78 atmosphere. So you see there's a difference in the value we got for the pressure. So for the real gas, you will require 9.39 atmosphere. For the ideal gas, if you assume ideality of the gas, that will be 9.78 atmosphere. Now, these are some examples you can try out on your own. Calculate the pressure of nitrogen gas at 273 Kelvin and molar volume of 22.414 liter per mole. Compare the results with that of an ideal gas at the same temperature and molar volume. So in this case, you are going to solve using van der Waals equation. Whatever you get, you solve using ideal gas equation, and then you compare the results and see the difference. Now, the second one says, calculate the pressure of a mole of nitrogen gas at a volume of 24.466 liter per mole and a temperature of 273 Kelvin. Find the pressure of the ideal gas under the same condition. Under the same condition. Liquefaction of gas. A gas is liquefied by lowering the temperature and increasing the pressure. Now, if you have ever gone to help your parents fill their gas, next time when they are filling that gas, touch the gas and tell me what you feel. You will notice that the cylinder will be very cold, very, very cold. So you see, at low temperature, the gas liquefies. So, and the pressure they use in filling that gas is always very high. They use high pressure to liquefy it. And when that happens, you will notice that the body of the cylinder is very, very cold. Now, at low temperatures, the gas molecules lose kinetic energy. They lose kinetic energy because they are not able to move about the way and collide with walls of container the way they used to and fill the whole space. So they move slowly, aggregate, and are converted to liquid. And at increased pressure, the gas molecules come together by compression and coalesce to form the liquid. So if you shake that cylinder, you will perceive that it is liquid. So it is when you use the what is it called? Regulator of the gas. You apply pressure that the gas, once you put it on, is turning, because of the pressure you have applied, the gas, the liquid gas, turns back into a gas, and in gaseous, it becomes gaseous form, which now supplies your gas tube so that you'll be able to cook. So it comes out in form of gas, not in form of the liquid. That is the work of the regulator of the gas. So the temperature below which a gas can be liquefied and above which it defies liquefaction, regardless of the pressure, is called the critical temperature. The temperature below which a gas can be liquefied and above which it defies liquefaction, regardless of the pressure, is called its critical temperature. So the symbol for critical temperature is Tc, and the formula for critical temperature mathematically is Tc, critical temperature, equals 8A over 27 RB. A and B are constants. R is gas constant. A and B are the Van der Waals constants. Now, critical pressure. It is the minimum pressure required to liquefy the gas at its critical temperature. Critical pressure is the minimum pressure required to liquefy the gas at its critical temperature. So the symbol for critical pressure is PC, which is equal to A over 27B squared. No, A over 27B squared. A and B, Avogadro's constants. Critical volume, VC, is equal to 3B. This is the volume occupied by a mole of the gas at its critical temperature and critical pressure. Critical volume is VC equals 3B. B is what? Van der Waals constant. This is the volume occupied by a molecule of the gas, its critical temperature and critical pressure. So here are some more questions for you to answer. Find the pressure in atmosphere of 20 grams of neon gas at a temperature of 10 degrees C, 10 degrees Celsius, and a volume of 22.4 liter, given molar mass of neon to be 20.18 times 10 raised to the power minus 3 kilogram per mole. (16) For a monoatomic gas, the ratio of Cp and Cv is, for a monoatomic gas, what is the ratio of Cp and Cv? Another question is that calculate the root mean square velocity of oxygen at 25 degrees Celsius. At 25 degrees Celsius. What is the vibrational degree of freedom? I talked about this yesterday. What is the vibrational degree of freedom of CO2 gas? Okay, we will have to work that one out. Determine the mean free path of CO2 gas molecule at 80 degrees C temperature and 0.2 millimeter mercury pressure. The diameter of CO2 molecule is 3.2 times. Now, what is the vibrational degree of freedom of CO2? So in order to solve that question, CO2 is what type of gas? It is a triatomic gas. Now, is CO2 linear or non-linear? This is CO2. It is a linear gas. It is linear. So if it is linear, how do you then, what formula do you use to calculate the vibrational mode that you have in CO2? Now we said if it is linear, it is 3n minus 3n minus 5. Now, since it is a triatomic gas, n is what? 3. 3 times 3 is what? 3 times 3, that's 9. So 3 times minus 5. So that will give us 9 minus 5. Sorry. Nine minus 5. So the vibrational mode will be equal to 4. Is this correct? Plus the formula I put here. And minus 5. Cheers. That's correct. Wow, we cleaned it. Okay, for CO2, triatomic gas, linear, we got that the vibrational mode is 4. So this is telling us that it has 3 translational mode, 2 rotational mode, and 4 vibrational mode of freedom. So that is how to calculate it. If it were non-linear, let's try for that of water. That of water. Water is not linear. So water is H2O. Now, water is triatomic too. It has 3 atoms, 2 atoms of hydrogen, 1 atom of oxygen. Now, it is non-linear. So water is not linear. It is non-linear. Now, I think the next lecture you will have atoms and molecules, you will be told why it is non-linear and why it has to bend like this. So water is non-linear, and because it is non-linear, to calculate the vibrational mode, how many vibrational modes you have, it's going to be 3n minus 6. Now, n is equal to 3. That will give us 3 times 3 minus 6. This will be equal to 3. So you have 3 vibrational modes. If you use this formula, you are calculating the vibrational modes. Vibration now. Okay, thanks. Three vibrational modes of freedom. Okay, so we have 3 vibrational modes. And when you remove 3 from 9, you have 6 remaining. Always you will have 3 translational modes. In that case, we have for water 3 translational modes of motion, 3 rotational modes of motion, and 3 vibrational modes of motion. So you could be asked, all you have to do is know whether it is linear or non-linear. And then Knowing whether it is linear or non-linear, which of the formula would you use? And then when you use that formula, you should be able to know what to do. Just know that N stands for the number of atoms. So you could have 4 there. It could be 4 atoms you have there. It could be 3 atoms, it could be 2 atoms, it could be 1 atom. So the question I asked you was for, I think, was it for a monoatomic gas? So you find out for a monoatomic gas. That means it's just 1 atom. So with this, I will unmute some of you, those who have been raising their hands. Let's see if you have any questions. Should have left it. Not all of them. Okay. Babajide, Israel, what is your question? I don't know. Okay.
Good afternoon, ma.
Good afternoon. How are you?
Yes, ma. My question is this.
Who is
Israel, ma. Israel,
okay.
ma.
Okay.
My question is this, ma. Under the derivation of an ideal gas, what I know is that an ideal gas won't behave, and the gas won't behave ideal under a high pressure and low temperature. A gas won't behave ideally under a very high pressure and low temperature. But the graph you were using to illustrate was like convincing to me. The graph you were using to illustrate was like convincing to me that I know that, and the difference between an ideal gas also and a real gas is that a real gas will liquefy and an ideal gas will never liquefy. So it's another difference between them. But when you are using that graph to explain, I was somehow confused. I couldn't understand
Which of the graph? The one for temperature, the one that involved temperature with one gas. With one gas.
Yes, the one that involves temperature, when you said if the temperature is less than 1, that the way I understand I know for hydrogen and helium, they are very close to an ideal gas behavior because of their numbers of molecules. They have very low numbers of molecules. So they are very close to ideal gas behavior at some certain point. But when you are talking about nitrogen, you were like, under that temperature, you said it will like have less than 1%. I don't understand that aspect.
Not less than 1. We said compressibility factor, PV over RT. So it's not as if the compressibility factor is less than 1, because if it is 1, then it's ideal. So definitely it has to be less than 1 because of the what do they call the molar mass of that? That is like 28 grams per mole, isn't it?
Yes.
Compared to all those gases, 28 grams per mole. So at that low pressure, you could see comparing we are plotting the compressibility factor against pressure. Against pressure. The compressibility factor against pressure. Against pressure. So what you see is that the compressibility factor at that low pressure was low because the dip came down. It was not on 1. Was it on 1?
It was not on 1.
It dropped down.
And that was what I was asking. Why the compressibility factor drops down? Because like I think the gas should be somehow far from ideal gas behavior.
Yeah, sure. That's what it indicated. Definitely. It dropped downwards, going to about 0.5 or more, less than that. So it's far from being ideal.
The gas,
yes, that's what we are saying. It was far. Take reference from the ideal behavior, which was 1, the blue one that was 1. So that's the reference point.
So the graph was like indicating that it was far from an ideal gas.
Yes,
Give you.
yes.
Okay. So
Yes,
my second
yes.
question is, man, this is my second question, man. The
Okay, sir.
vibrational, let me first ask this.
Mm.
Why are we using R as 0.8? I thought R should be 8.31, 8.314. So
Where?
in a our gas molar constants,
For which one? For which question?
the one I know, the R I know was supposed to be 8.31, but you are like introducing
Okay, no, I'm
0.082.
not introducing. You have to, depending on the units, yeah,
Okay,
or
I'm
what you have
using.
been asked to calculate. Yes.
Okay.
So you have
Okay.
8.314 joules per Kelvin per mole, isn't it?
Yes, that's true.
Then there's one in liter atmosphere per, I just mentioned it there.
Okay, I've understood.
Yes,
So if
yes.
you are
So,
given liters, if you are given volume in liters and R is
yes,
included in the formula, we know that you are going
yes,
to use the constant that has liters.
that has liters. If what you are
Yes.
looking for is like we were looking for pressure, isn't
Yeah,
it?
ma. Yeah, ma.
Pressure in atmosphere. So
Yeah,
you
ma.
cannot be using the R that has 8.314
3, 4.
joules per Kelvin per mole, because there's no room for atmosphere there. There's no unit for atmosphere there.
Atmosphere
There's no
there.
unit for
Okay.
pressure.
Oh, you're
Yes,
there.
there's no unit for pressure there.
Pressure there.
So
Okay.
because this one has a unit for pressure, especially for that, what is it? Van der Waals constant that
Oh,
we
constant.
Van der Waals
Right.
equation, yes, that we
Okay.
used.
Okay.
You were asked to
Okay.
calculate the pressure. Now, looking at
Okay.
everything there was nothing to take you to the pressure, or after doing
Okay.
your calculation, you will get in pressure. So that's why
Okay.
we had to introduce that aspect of R that
That has an
incorporated pressure.
atmosphere.
Yeah,
Okay.
exactly. So that's
Okay,
it.
man.
That
So my last
incorporated
question is
pressure.
this, man. The last question is
Hey,
this, man.
only you.
The we are discussing about the vibrational mode and all these kind of modes, yeah. So we are talking about
Yes.
if the gas is non-linear or linear. So we have to use the idea of our shapes of molecule to know the gas, if the gas is linear first or non-linear, before we now apply our formula to it. Is that the way
Yes.
you have to do it? We have to use our knowledge of shapes of molecule first to know if the gas is
Yes.
linear or non-linear.
Yes. Sure.
Okay, ma. Okay, ma. That's all, ma. Thank you, ma.
You're welcome.
Yes, ma.
Yes. One more before we go. Yasin. Yasin. Still muted.
Good afternoon, ma.
Okay, good afternoon. What is your question? Oh, it has muted you.
Ma, for non-linear gas,
Mm-hmm.
their rotational mode,
Yes.
and this is it constant? Is it constant?
They are for all gases.
Yes.
Their translational mode is constant.
It's constant.
Mm.
Okay, so
translational
mode is constant, and the other. But once we get the vibratory, we know that for non-linear is 3 for translational.
Whatever is remaining, once you get the vibrational, you know that what is subtracted. Okay, if you subtract the vibrational, what is remaining, you share for the rotational and translational. So the translational is constant. You know it's 3.
Yes, ma'am.
So whatever is left, it could be 1, it could be 2 that will be left after removing the vibrational or after calculating the vibrational. So after, let's say you have 9 take away 5, isn't it?
Yes,
9 take away 5, if it's triatomic, 9 take away 5 is 4. So 4 vibrational. So out of that 9, 5 was used. The 5 that you have there is for what? Translational and rotational.
Rotational.
Yes. You know, it is
Okay,
5 plus 4 that will make up 9.
Yes, ma'am.
So now you know that translational is 3.
It's 3. It's
Whatever
always
is
3.
remaining.
Whatever
Yes.
is left, just add it to the rotational.
Yes. Yes.
Okay. In the first question I asked us to solve, there's no value for A and B van der Waals constants.
Okay.
No value for them.
What gas did I give to you?
I think one has nitrogen and I can't remember the other one. There's no constants for them.
All you have to do is go online or get a textbook, chemistry textbook, physical chemistry textbook.
Okay.
Check for the gas constant, the van der Waals constant for those gases. Then you use it.
Okay, ma'am.
But you will always be given in the exam hall.
Okay. Thank you very much.
Part of the work you do. Okay.
Okay. Thank
you. Yes. Please, for the others. Okay, I shouldn't still. Okay. So let's unmute another person. Is this one? Samuel. Is he on it? Samuel. Okay, let's try Ayondele. Is it difficult to unmute? And it's not, it's still the same. Okay, you have. Samuel, is that you? Okay, Ayodele. Makinde. Makinde, what is your question?
Please.
Hello.
Mode, man. Hello, can you hear me, man?
No, I can hear you now. Maybe start afresh.
Please, how can we calculate translational and rotational mode, man? Because I know only of that vibrational mode, but
once you know vibrational, you have gotten translational and rotational.
But man, for helium, you said the rotational is 0. How did you get that 0, man?
Now, helium, is it a monoatomic gas or a diatomic gas?
Monoatomic.
Monoatomic. So,
yes, sir.
Monoatomic is linear. So we use linear. 3 times 1 is what?
Network is looking me over.
Sorry,
hello,
3
man.
times 1. Can you hear me? 3 times 1 is what?
It's 3, man.
3 times 1 is 3.
Yes, man.
What is the formula again? Since it's monoatomic, well, it's not linear or non-linear, isn't it? It's not linear or non-linear. So it's just, it's monoatomic 1. So it has only, for all monoatomic gases, it has only translational motion, which is 3. I told you translational motion is constant for all of them. So it has only translational motion, which is 3. That's 3n.
Yes, ma'am.
Just 3n. Because it is not linear or non-linear, it's 3n. So 3 times 1, 1, which is what? 3 translational motion. So rotational motion is 0, vibrational motion is 0. Is that okay?
Okay, ma'am. Okay, ma'am. I understand, ma'am.
Mary.
Good afternoon. Please, I didn't really understand the graph of when you were talking about the graph that illustrates the behavior of gases on ideal, like when they don't behave like ideal gases. I didn't understand the graph.
You don't understand the graph. We have to go back
Yeah.
to that graph. Do you have the graph with you?
Yes, ma'am.
Hmm? Can you see the graph?
Yes. Yes, ma'am.
Now, did you see the one going, did you see the line that goes horizontal, straight?
Yes, ma'am.
You saw the horizontals. Now, that we are taking, what, remember, we said the compression factor, PV over RT. Compression factor, PV, I have a lecture. PV over RT. Z is compression factor, which is equal to PV over RT. So we could as well say Z there instead of PV over RT. Could as well put Z there. Now, the one that goes to, if you calculate the compression factor for an ideal gas, it's supposed to be 1. So that's why you have the horizontal line there at 1. Can you see it on the graph?
Yes, ma'am.
Okay. Now take nitrogen. You can see for all the pressure, 0, 200 atmospheres. I don't know if that was what was there. For all the pressure, the ideal gas was constant. It was constant. Now take nitrogen. For 0 pressure, that is, go to x-axis. I'm talking based on x-axis now. For 0 pressure, you can see that it started decreasing from 1, isn't it?
Yes, ma'am.
And at a point, even at maybe 100 atmosphere, there was a dip. Let's call it, there was a kind of valley in the curve, a kind of valley. This is telling you that it is deviating. Your reference point is the ideal gas, which is horizontal at all pressure, given a compression factor of 1. So from that particular 1 that you have there, look at the nitrogen. As you are increasing the pressure, what is happening? As you are increasing the pressure, it is decreasing, the dip is getting deeper, isn't it? And at a point, at a very high pressure, it went up. It went up, deviating completely. So in both sides, both below 1 and above 1, it is far from ideal behavior. That is what we are trying to show here. That at all pressures, it is far from behaving ideally. There is no point in which it was almost 1. Like if you take the hydrogen now, if you take hydrogen and you are going through the pressure, there was a point at which it was almost 1 before it went up again. And if you take helium, the same thing, before it went away. So we are using, the reference point is that ideal point. That for those gases, their compression factor is lower. For some of them, it's far lower than 1. For some, it is higher than 1. And as long as it is not 1, that is a deviation from ideal behavior, whether negatively or positively. Negatively or positive, what it means is that maybe by repulsion or by attraction, the gases deviate from ideal behavior. So that is what we are trying to say. Do you understand?
Yes, ma'am. Thank you, ma'am.
Okay. Thank you. Thank God. Okay. So we will end the class. I don't know. I am through with the course now, but I'll just give you some questions. We'll solve some questions on Thursday. So see you on Thursday.